Okay, we'll go ahead and get started. I'm sure people are going to trickle in. As you may see, I'm sorry for you. It probably might get in your way. I'll try and write hi, but as you can see, I'm going to attempt to record this because more and more of your fellow students are falling to COVID. Right, it's happening. Fortunately, our department is doing better than most others. Actually, we're doing okay. We're hopefully able to stay in person, right? And learning online is really hard. Otherwise, there would be lots and lots of engineering schools online, and there aren't. And it's because it really sucks to learn engineering online. So I'm optimistic. We'll see how this goes. This class, right, I'm going to pick up kind of reviewing and then moving forward. And then I think next week on Monday is actually going to be lab. So for the next couple of weeks, we're going to be flipped because this weird extra Monday holidays that we have. So pay attention to announcements, and realistically, you'll be fine, right? If I'm not here when class starts, probably downstairs and vice versa. They're not too far away from each other. Did we have any issues on the homework? Right, the first homework, yeah.
I just like with the Venn diagrams, I'm not sure if I did them right. Like if I were to draw it out on a table, I'd know which, but like coloring on the Venn diagrams, I just wasn't sure if I.
Okay, so I'll say with the Venn diagrams, I'll do one. Actually, we can do one of those just to kind of talk about it. But the point with the Venn diagrams is to give another way of learning and understanding digital logic. If the tables are good for you, then you're set, because the tables are a better tool. But some people struggle with it, right? So I want kind of alternative ideas of ways to communicate this fundamental concept of digital logic, because it's hard, right? You haven't done stuff like this in school unless you had a digital circuits class in high school, which I don't think happens for very many students. So let's talk, right? Venn diagrams. So the concepts are, if I have variables A, B, and C, right? These are variables, which are usually tightly linked to signals, right? Usually when we're using a variable, a Boolean variable, right? Because each of these are just true or false. What we want to communicate is what is happening with them. Well, what we're getting at, the most important concept for all of these is, of course, the gates, right? Where this is and it is true if A and B, then the output, which we'll call C for now, is true, right? Generally, when we say true, we mean 1, right? It's a 1. And 1 translates to an analog voltage, which in the case of like our lab that we did last week, on is 5 volts, right? If you're using TTL, or that we're actually using a CMOS technology, but it's 5 volts. So when I say true, I mean 5 volts. It's possible, right? If you've looked at your books, I post the chapters where it might have a signal called A dot low, and that's saying that true or on is actually a 0 because it's an active low signal. I don't focus very strongly on that for you because I think it adds a lot of overhead for you and it gets confusing, but I need you to be aware so when you go read the book, you understand what they're talking about, right? I'm not going to ask questions on the exams, certainly, about active low circuits, but I want you to be aware they exist, so when you read them, it makes sense. All right. Similarly, we have an OR gate that is true. It turns on the output if either A or B is true. And this is non-exclusive. A and B both being 1, the output becomes 1, right? And the way we describe these is through truth tables. And for now, we don't have to worry about counting very much in binary, right? We just know this pattern is the first column alternates every other one. The second column repeats twice. The third column, if there was one, every 4, right? Because anything digital is going to have this 2 to the n location. In relation to us, n usually means bits. So 2 to the 3, if there were 3 different signals, would be 8. There are 8 rows, right? That's all this is saying. Well, in this OR gate, we only have 2 variables, therefore 4 rows, 2 to the 2 is 4. And then we just say it is true, C, right? I can use the variable, or I can use the expression or, right? That's the operator, or. The C and or are the equivalent, right? In this case, it's true in all 3 of those situations, making this not true, or 0. Now, when we go ahead and look at this for a more complicated circuit, we can do something like here. I can call the output F just to get far away from A, B, and C, right? And the variables are just names for them. I can use more than one letter if I wanted, right? I could call it Bob. This could be the signal Bob, but I just use B because I have terrible handwriting and I don't want to make it any worse on you than it already is. So what we say is, well, I can write a Boolean expression for this. We've kind of talked about this, where I have the words and, or, Nand, which is not and, right? Which if I drew the truth table of the and gate, it's the Nand is just anywhere there was a 1 becomes a 0, anywhere there was a 0 becomes a 1, right? Because of this bubble is an inverter, right? Inverting means just turn 1 to a 0 or 0 to a 1. It's truth table. It's really simple, right? There's only 1 input, so 2 rows, 2 to the 1 is 2. There we go, right? So that bubble represents this inverter. Inverter, its word is not. Don't do that. The other way of writing that is on this A, I have A. Another of doing this is B is equal to not A, right? That's what the bar over it means, is not A. These expressions, when I do them, A and B, right? This is an AND gate. I'm going to use an intermediate signal. I'm just going to go ahead and write it out. A, B, C. I'm going to call this D and that E, right? Even if I don't give you these names, you can make up a variable for them to write an intermediate expression that says D is A and B, because in Boolean expressions, multiplication is AND. Talked about this last time in S, you remember? Yes. Similarly, E is equal to B and C. I do not need to put the explicit multiplier dot, right? That's B and C, same thing. Well, F is the OR operation of D or E, right? It doesn't have to know necessarily what A, B, and C are doing. It just has to know what D and E are doing, but there's a relation. So we can go ahead and do a substitution, which is equal to A and B or B and C, right? That's the expression. The OR is the same operator if either of these are true. So getting to the question at hand, which is, we don't understand Venn diagrams. Well, some of us do, some of us don't. That's okay. I have this expression. I want this to be true in either case. So what I do is I look at the overlap between A and B, right? So A and B is going to be that, because it's part of the circle that shares those, right? That's the expression A and B. This whole circle, it doesn't care what C is doing. There's no C in this part of the expression, or term as we're going to call it. So that is A and B. Well, then we say, where does B and C overlap, right? Where do they share? Where do I have both of those? Well, the section that is B and C is right there. And you'll notice that both of them share that inner bit. And that inner bit is actually A and B and C, right? But that's not in the expression. It's okay, because it's covered twice. There's nothing wrong with covering something twice. It just kind of implies that maybe there's a simplification. There's not in this case. This is actually simplified. But if you have lots and lots of overlap, maybe there's an easier way to write this expression, which is what we'll talk about in the second half of this lecture, is how do we find that simplification, right? But for now, we just have to understand that those two, and because they're OR, because it's an OR expression, I get to color in all of it because I want it to be true if either of those statements is true. That's what OR says. Well, this expression method where I have multiplication ORed with multiplication is something that we call sum of products. It's the sum of a bunch of product terms, SOP, sum of products. This is an important term. This is an important idea because it's going to come around a whole bunch. In fact, you're going to see why this lecture, and then it's going to repeat because it turns out it's really easy to design circuits, good circuits, that take this form. The other form that is easy to design is product of sum, which is that, right? Product of sum, product of sum. We don't use these as much because they're annoying to simplify because you have to pay close attention to algebraic simplification, right? If you were to, as far as you know, right, you've taken algebra. I've told you this is multiplication and addition. You can treat it as such. So you can imagine that you're just going to FOIL that, right? It's going to be really annoying, but you're allowed. And we'll cover that later today. But for now, just understand this is a form of expression that represents product of sums. It's circuit topology. Right? So this intermediate signal that is the output of the OR gate to the input of the AND gate, that is D is equal to A or B, right? That's its inputs, its output is D, which is A or B. This is B and C, so E is B or C. Then the final output F is that, because it's F is equal to D or E, which is equal to A or B, right? Because that's just D. And then E is B or C. Okay, so then we have to go ahead and say, well, what is this Venn diagram? This is the harder of the Venn diagrams to draw. Because now what I have to do is go and look at the AND situations as well as the OR, right? So this first circle, A or B, is really big, right? Because the OR is all of that, all of A or B. And then the E term, which is B or C, is all of that, right? Two big circles that, well, two terms that each take two full circles. And now I have to, after identifying the two possibilities, is where do they overlap, right? That's the AND statement. So I've taken care of my ORs. It is A or B, and B or C, but where is it true that both A or B and B or C? Well, let's see if I can't find a different color. Oh, there's green. Well, over here, there is no red, so it's not helpful, right? And up here, we have red and blue. Down here, we have red and blue. So down here, there's no blue, right? So that doesn't help us. So what we want to do is anywhere that there is both red and blue, Sorry, gotta think. I drew this a little bit wonky. I gotta fix it so it's clear. Oh, I lost my red. So this region has red because it is C or B. And it has blue because it's A or B. So this is both red and blue as well. So we flow through here. This inner circle, well, we can evaluate, right? Is it both B or C? Yes. And there we go. That. Right? That's the overlap. That's what we're looking for, is drawing the two weird circles and saying, all right, that's what overlaps. There's another way of doing this in this particular case, right? So once we start to understand things, which is I could say, well, B is in both of the terms and it's ORed. So I know that all of B is taken care of, and I could just start with that and say B is the whole B circle. And then I just have to look at where is the rest of that, right? Where is that overlap? Don't worry about necessarily the shortcuts, but I want to show you some of the things that you might be aware of as we learn and develop. Does that make sense how I got that one? That's all Venn diagrams are doing, is they're giving you an illustration of how these expressions work, right? What do they cover up? And I could do the same thing, it turns out, with a truth table, if that's what you like. So the way that you would do a truth table is I would say I have this expression for A, B, and C. There are three variables. 8. And then we want the expression. I'm going to break this down. Where is A or B true? Where is B or C true? And we're calling this D and this E for shorthand so that I can say, where do I have D and E? Okay. This is the power of truth tables. Well, let's go ahead. I'm going to write 1 anywhere A or B happens, right? If A or B is true. Yeah, quick.
So over here, did you make a mistake and put a plus between the D and the E after F? Is that supposed to be a plus?
Oh, I did make a mistake.
So isn't that just, yeah.
B and E. This is still correct. That was the wrong step.
Okay.
Thank you. Good catch. Does that make sense, everyone? Why that was wrong? Okay. Now what we're going to do is A or B true. B is true, so I get a 1. B is true, so I get a 1. A is true. A is true. B is true. A is true. Now the B or C, 1, 1, 1, not 1 is 1. So I'm gonna put a 0 there so I make sure that my bad handwriting doesn't mess me up. And there we go. Okay. Now the step is just like I did, right? This is all I've done is I have colored in the A or B. I have colored in the B or C. Now I find where they overlap, and that happens here. Doesn't happen here, right? There's a 1 and a 0, and then all three of those. So what that means is on my D and E expression, there I go. That last step makes sense? Where I'm just looking at the and terms to fill in the ones. And we're going to do this a lot, potentially, right? Is anytime I have these intermediate signals, I need to know what they are. I just write them up in a truth table until I get to the final end result. And I'm going to introduce this lecture another tool for doing the same kind of thing.
Real quick.
Yeah.
What do you find more convenient?
I do this all the time because it's really obvious, in fact. What you're going to find throughout your engineering careers is there going to be a few tools that you find useful all the time. So like if you've taken chemistry, for example, you get really annoyed because they make you do a whole bunch of unit conversions all the time. Turns out we do that all the time as engineers as well. So, but yes, I do find this very helpful when doing circuit analysis. Okay, I'm going to try and stick on this board as much as I can just because it's better, more well lit for my recording, but I'm going to spill over when it's convenient. If I ever start erasing something that you need to not be gone yet, just yell up. It'll be okay. So I'm going to pick up some more review, right? So this is kind of the analysis side, right? Where we analyze what's happening to a circuit. I kind of skipped right into that because it ties into the Venn diagram really well. So let's go ahead and move on to kind of the design side, where design is we look at one of these Boolean expressions and we turn it into a circuit, right? And there's a couple different ways we can do that. And I'm just going to walk through the design process for a real problem, okay? And the real problem that I'm going to do, let's see. Yeah, let's go ahead and start with this one. Let's say that we have a circuit that we want to design and it outputs true if reset. Okay, let's say we have a system that has 3 inputs, A, B, and C, and I want to output true if 2 of them are true. And let's go ahead and make up like a real situation, a real situation where you might do this. And the off-the-cuff example I came up with last time I gave this lecture was, let's say you have like a hazmat situation and you need to make sure that the hazardous materials on one side never get a straight shot all the way through your decontamination zone to the other side. So we're going to build a 3-stage door, right? Where your goal is 2-stage decontamination. You open this door, you step in, the door closes. That step, right, you walk through, it's the airlock, right? You ever watch sci-fi? But this is just a 2-stage airlock. And we want a circuit that says, if 2 of these doors open, lock the 3rd door. No matter what happens, that 3rd door cannot open if the other 2 are open. So my signals A, B, and C are going to be true if doors A, B, or C are open. That's all they're saying is this door is open. So I write up the truth table. And then, well, I'm gonna use L for lock, right? It's gonna lock the other doors. None of the doors can open that aren't already open. And then we're going to say that, well, I don't need to lock them if none of the doors are open, right? I have a door, only one door, and I can jump down and start finding anywhere there's only one door open, and I know that there's no problems, right? And then I can find where there are 2 doors open, and I want to turn on my lock because I don't want that 3rd door to open. What do I do in the case that all 3 doors are open?
Run.
What do you think? Run's a good one. What do you think?
So are you saying like if L is 1, that means it's locked, right?
Yes.
Okay.
Yeah. So this situation, we said I want to design a circuit that this never happens, right? So I'm going to introduce this new idea. We'll come back around to it. And it's, we don't care is the idea, right? Is I don't care what happens here. I don't care what lock is doing if this has happened, because something much, much worse has happened, right? And so we symbolize don't cares with X's. And all a don't care means is I get to choose whether I want that to be a 1 or a 0. I got to choose whatever is more convenient, because later we're going to use this to simplify it. And if there's a situation that shouldn't happen or can't happen or that kind of thing. I don't have to design the circuit with that in mind. I'll just choose whatever's convenient. Okay. Okay. Well, let's look at this and say, all right, I need to turn this into a circuit, right? Your boss told you to build the circuit for you. Let's figure it out. What do? Well, it turns out that this is really easy because, did I mention the word minterm last time? It's okay if not. I mean, I just wanted to check because sometimes I say things ahead of time. So we're going to introduce a new concept here. And what I'm going to do, right? We've already done truth tables. We've already done some of this. So I'm going to mix review with new stuff. So all minterm means is any row of a truth table that has a 1 on it. So this is a minterm. This is a minterm. That's a minterm. Those are my minterms, right? Those rows are my minterms. And the way that I can express this, and this is really nice because we're lazy when we write textbooks, right? So we want to invent a way that we can express this in a simpler method. And what I'm going to do is say that L, which is going to be a function of A and B and C, not the logical operator A and B and C, right? It's just the function. So it's like f of x, right? It's just a function, is equal to the sum of my minterms. Well, these are going to have numbers, and I'm actually going to have to do a return down here so I don't run out of room. Where these are rows 0, 1, 2, 3, 4, 5, 6, 7. There are 8 rows, but only 7 numbers because we are 0 indexed. Okay, always remember that. We're going to be what's called 0 indexed. We're going to start counting from 0 because we want to know that there is nothing there, right? Okay, so we're 0 to 7. My minterms, the places that my 1s are true, because I'm going to take advantage of this, don't care, and say that it's 0 because it's going to make my life easier, right? And I'm going to say 3, 5, 6. You may also see this if your professor is less lazy than I am, where you're going to do M3, M5, and M6. It conveys the same information, right? I know that this is minterms if I've done the sum of the mins, but that's all this little lowercase m is. We're going to get a thing called max terms. I bet we could guess what a max term is, right? Is any row where there's a 0. But let's look at minterms. These are we're going to use this a lot more. And all it's saying is, well, sum, addition, okay? It's giving us this hint. So this minterm of this guy is shaped like, well, I erased my sum of products, right? But it's just going to give me a sum of products, it turns out, where L is equal to I have 3 minterms, so I have 3 1s. I'm going to put up 3 minterms. All of my minterms have every single variable in it. In this case, I have 3 variables, A, B, and C. And now I just go look where the zeros are. In my first minterm, minterm 3, I have a 0 for A. That means I say not A. And all this minterm is saying is L should be true if I have a 0, 1, 1. See that 0, 1, 1? Or if I have a 1, 0, 1. Or if I have a 1, 1, 0. Right? Does that make sense? For reals, make sense? Okay. Now we need to build a circuit, right? I've got an expression. Let's build a circuit. And we could build, right? We could build a Venn diagram off of this where we draw 3 dashed lines and any one of those sections gets filled in. This one, we get a cheat because I know this is a sum of products. Anytime I use a minterm, I'm going to get a sum of products expression, which means I'm going to get a circuit whose final output is an OR gate, So now we can start building circuits, right? And I have three terms in this that are ANDed with each other, that are AND gates. Each of those AND gates have three inputs into them, right? And a 3-input AND gate, all that means is it is true. It puts out a 1 if all three of the inputs are true. But there's a bit of a complexity, right? Because the A is not A, rather than A in this case. So sometimes how you'll see this drawn will be something like this, is I'm going to have an A, a B, and a C. And this first one, I need to make not A, right? I've just inverted it. If this is A, that's not A. And now I have a gate that says if not A and B and C, right? Because if I have a 0 on A, that makes a 1 on this side. And then I get 1, 1, 1. It makes not A and B and C. We do the same thing here. And there's two ways that are perfectly fine to draw this. One of those is I draw really messily and I say, let's take C. Not B. See those little arches? That just means I want to be very clear that they're not connected, so it's jumping over the wire. So this is now C, not B, A. A comes from here. There we go. We can see that this can get really messy really quick, right? Especially if I had 4 ones in this. So oftentimes what you'll see is you'll shorthand it. Like so. This is what we call virtual connections, right? We know that this A is connected to that A because I've named them the same. If they have the same name, they're the same thing. Like in lab, right? When we had digital signal on one page and digital signal on the next page, and we understand that that's the same digital signal because it shares a name. The problem here is I've written just not C, right? And there's an implication that there's an inverter between C and not C. But I haven't drawn it. And you're gonna see this all the time, where we don't explicitly draw the inverter, we just say not C. But there's a problem here. There's a trap, I should say, in that in an ideal world, that's fine. But in a real world, when we change values, right, these gates take a little bit of time to change. And that means there's an inverter here that I don't see. And so there's gonna be a delay that I don't see. This is gonna become important later. It's not important yet, but I want it to be prepared. I don't want you to think that these are ideal circuits. They're not perfect. They have problems in them. And I don't want to surprise you with that down the line. I want to be aware that there's a reason that you might draw it like this, right? To be explicit about your inverters. Besides just being lazy, right? Okay. Where was I? Yes. Next design example, because this is done, right? If this output is L, I have designed a circuit that will keep the world safe from my hazardous materials. That's your design process. We're going to give you better tools for this, but this is one way of doing it. The problem is that this does not necessarily give you the easiest circuit that you could make, right? And that's what I'm going to build up to today, is that's where we're going to end up, is how do we find the easiest circuit? And of course, later I'm going to teach you an even better way to find the easiest circuit, and then an even better way, right? And I'm going to torture you for this, but it helps you understand the tools. Understanding this will help you understand the tools that I'm going to give you, so that it also helps you understand how to avoid the problems of these hidden delays, right? That's what we're building, is not just how do we build a circuit, how do we build the right circuit, okay? So new story problem, if I can find my eraser. I'm whispering. Do we have questions? I want to make sure we're just talking. It's fine. I'm not mad. I just want to make sure that we're not confused, right? Because you talk to each other all the time. I'm not judging. I just want to make sure we're not confused. I know staring at my back's not super interesting all the time.
So there's some cases where you use the max points.
Yes, there are times when you would use the max terms. And in fact, this next example is going to be fun because it's going to show you a perfect example of when you really, really wouldn't want to use a max term. So we're going to go approach it from the opposite way, which will be really funny, but I think it'll work. And I'm going to rename my variables from A, B, and C. And what I'm going to give you is another kind of real circuit, right? The kind of thing that you might go and design. Because if you've ever watched a movie like, I guess The Italian Job was one my students told me, where they hack into a computer and they tell all the lights in the cross traffic directions go green so everybody runs into each other, causing a traffic jam. Well, guess what? It turns out that many, many light systems are designed in such a way where that's physically impossible. You can't do it. And you can do it simply, right? Because if I have a signal called green, north, south, and that turns my lights from north, south green to, my north, south lights become green. And I put that through an inverter, and I'm going to call this a enable my east-west green signal. Okay, and then the thing that turns on my east-west would be an AND gate that says enable east-west and green east-west. Oh, sorry, east. So that if this is green going north and south, that means I have a 1 here, which means I have a 0 here. And I have this virtual connection, which puts a 0 here. And if this is turning on my light, right, we can use an LED just like we did in lab. Well, a little different, right? Well, if this is 0, this light can never turn on, right? Unless something breaks, but we're safe. We can never have a green on north-south and have the east-west light turn on, right? We built a foolproof system. Well, barring like weird electrical failures, but this is the real type of idea that we use in traffic light design because of the massive amount of fatalities you could have if someone could hack it and turn everything green, right? As basic is we can build it so it cannot do what they did in Italian Job. But let's build up a little bit more simple or more complex signal. Let's say we want to keep with the traffic light example and say, I want to design a circuit that will request the other direction to stop being green so that I can become green, right? And so if you go down like, I'm not from Ogden, so I don't know exactly. I bet Harrison is a great example where if you're driving north-south on Harrison and late at night, the crossed lights will never change color until a car pulls up to one of them, right? So a lot of those, one of the methods I should say is to have a pressure detector, right? P says there is a car here. And my output is going to be R for request. Hey, let's send out a request that says, I would like you to stop being green. That's all R is doing. Because I want to become green, and I can't do that if you're green. Okay, so the next one is, well, I'm never going to bother sending a request unless the other one is green, right? If it's not green, I don't need to bother asking the question, could you stop being green? And my other one is a timer. And the timer says, I need Harrison to stay green for the majority of the time, right? Because that's the majority of the traffic. So don't send the request unless I've been green for a long enough period of time. So green timer is basically, for me, is going to be an active low signal, okay? Because what I'm going to say is the timer is running if I have a 1, and if the timer is done, it drops to 0, okay? That's going to be my definition of what timer is doing. And if we need to understand what our signals are doing, okay? Well, when do we want to send a request? When should we ask it to stop being green? And take just a minute, like 30 seconds, to fill in your ones. Figure out what do you think, when should it send out R? When should R go to 1?
And just to clarify, the green column, that means that the other light is green.
Is green, yes.
So when it's 0, the other light's off.
Yes.
Or red.
Or at least not green. It could be yellow, but yeah. Okay, it looks like the majority of you are done thinking. So let's go ahead and walk through this, right? Because I want to point out some interesting things that you can do, right? So P is the pressure plate. Again, we're prioritizing the other direction. So what we're going to say is, if there's no car, why would I send a request, right? I don't need to become green if there's no car. So I instantly get to write zeros on all of those columns, right? Nothing else matters if there's no car. And now we're just going to step over to the next column. And I like doing this one column at a time, right? Because this column is grouped in big chunks. So if I get to say some big sweeping statement like that, then I'm taken care of. And I kind of cheated because I knew that this was going to happen, that I ordered them this way. Because I could do the same thing with timer though, right? Because if the timer isn't done, it's 0. Same thing for green. We say if the other direction isn't green, why would I ask it to stop being green? It isn't. So what I do is I go look and say where we're not green, add a couple more zeros. And these would be zeros too, right? But there's no reason to write zeros twice. I'm already covered. There's only one column for that signal. And then I look down here, the timer. So the timer I specified is 1 means the timer is running. 0 means the timer is done. If you flip this up, if this is the only mistake you made, great job, because it's a little weird because of the way I defined it. But that means here the timer is done. I am allowed to send that request. Here though, there is a pressure plate. The light is green, but my timer is not done. 0, not done. Okay, so here's a perfect example where I get to say that R and I'm gonna drop this parentheses really quickly, and because again I'm lazy and it takes a lot of writing, but we want to remember that R is a function of input variables P, G, and T, right? And the order actually matters, because if I write the sum of the minterms, right? Sum of the minterms, and the minterm is this one, which is 6. There we go, right? There's only one, it's great. But if we change the order of P and G in my truth table, I actually change the location of the 1 potentially. And I've kind of broken my truth table. So I need to know what the order is. Most of the time it's kind of obvious essentially, but just be aware that's why we put the order. And then we go ahead and say, let's build the circuit. This is like the easiest circuit we could possibly have for a 3 input because it's just one minterm. And that minterm is 6, where it's P, G, not t. I said there's a sum of products output, right? But the OR gate, there's no OR, so I can just not use it. Make sense? There we go. I built a circuit for this. Now, to get to the question that was asked earlier, that I said is a really good point, I get to introduce max terms now. Because I don't want to overload you guys with too many definitions all at once, but now I think is a fine time. The way that we write max terms is that, and we say max of, well, in this case, it's just everything that isn't a min term. So there we go. Now, the expression for this is a little bit more complicated, and I am not going to write out the whole thing because there's a lot of max terms, right? So this is the max term expression, and I get to say it is equal to something. Well, in this case, it cares what the zeros are. Okay, the min terms care what the ones are doing. The max term cares what the zeros are doing. So what I do is I go over my truth table and I said 0. So this 0 term is going to become P or G or T, because the sum of products is what results from my min terms. The product of sum is what results from my max terms. Okay, and we can get into the theory of why, but I'm not going to. We just accept this for truth, okay, for now. And just you're flipping your gates. But the other thing is, where are the zeros, not the ones? Well, P, G, T are all 0. That means they don't get any not bars because they're zeros. Okay, it's just flipped. I flip the AND gates to OR gates, and then I start building it. And I need 7 of these product terms, right? Because there are, or sorry, sum terms, and they are product together, product of sums. On the second row, there is a 1 on T for timer, which means it gets a bar. It's not T. The third one, which is row 2, right, is 0, 1, 0. So 0, 1, 0. And I continue as so, such that 7, the last row, which is also a 0, is all ones, so they all get bars. They're all not that, okay? Because it cares what are the zeros doing. That's all the max terms are. Min terms, max terms. Min terms, where are the ones in the truth table? Max terms, where are the zeros? And now you can see why you might choose the ones or you might choose the zeros, right? Because if I choose the ones, I get 1 AND gate and nothing else. If I were to choose the zeros, I get, well, a lot, right? I need an AND gate that has 6 inputs to it. Sorry, 7 inputs to it, and I need 7 3-input OR gates. Right, one of those is the right choice. If you had the other one, which would be 1 1 1 1 1 1 0 1, right? If we had the inverse of this, if that's what we were designing, then we would probably want to choose the max terms, because then I would end up with only 1 OR gate, which is much better, right? So there is a right thing to choose as far as designing your circuit, and there is a reason that you might choose one over the other. So good question. Yes.
So when you do design it, whether you use the max or min term, it does the same thing?
It does the same thing. Yep. And what's nice is we're going to go ahead and talk about how to convert between the two. Actually, we can convert between the two, and that will be in this lecture later. There's a whole theorem around doing this. Yes.
You had mentioned that if you change the order, you change the number on the min term.
If I change the order of my variables, I change the order that I write this.
And so the 6 would be a different number.
Yes, because if I changed P and G, right, then P is doing 0, 0, 1, 1, yeah, this, and they flipped. And then I have to find not 1, 1, 0, but well, in this case, it actually doesn't change, right? Because it's still 1, 1, 0.
Right.
But if I change G and T, then I'm looking for 1, 0, 1.
Would that change the answer at the end? Or-
No, you'd end up with the exact same circuit.
Okay.
So as long as you keep this and that straight,
Mhm.
everything's fine.
Okay.
If you change this and don't change that, then we've made a mistake. Okay. And guys, I know you're new to school, most of you, and you're afraid of being wrong. If you ever get confused, it is really important that you let me know. Even if you can't speak up in class, send me an email, come talk to me in office hours, right? I need to remember, I'm gonna go check, I'm gonna write this down real quick because I keep forgetting. I'm gonna go check the poll, right? You guys filled out the poll for when office hours are good for you guys. And I'm gonna go look at it, see if I need to adjust my office hours. I don't want you guys to use them, right? I don't want you guys to be confused. And so I've talked about analysis, right? Where we just look at the circuit and we write out the intermediate signals and we get them and we build up on each other so we can use a really complicated circuit in order to, or we can analyze really complicated circuit by just breaking it down into blocks, right? There's something that I need to introduce now because everyone gets confused on it. I'm not sure why. And so you're going to see me talk about this a lot. I'm going to try and keep this short. And I posted a video on it, right, to Canvas. I sent out an announcement with like 3 short videos that kind of help you through if you need some reviews on specific topics. I think, unfortunately, on the Canvas page, I just called them video 1, video 2, video 3, or something like that. But if you click on them, the titles of those videos will tell you what they're about. Okay, and that I will post more of those videos to my YouTube channel. In fact, there are YouTube videos of my lectures going back a 1.5 years now, I think, that you could go watch. The issue is that I've kind of reorganized them because if I was doing it the way I used to, what would happen right now is you guys would basically know how to count in binary and add binary numbers together, and you'd still be wondering why this is a math class and not an engineering class. And as is, I feel like I could go ask you guys to design a circuit and you guys could do it, right? As long as it was simple, right? Within your abilities, you guys are now digital circuit designers. You can go build simple things, you know how to do things. And now we just want to learn how we can do them better. But one of the things that we have to learn first is how we talk about circuits, okay? And what I want to introduce is this concept of block diagrams, because I've already started using them. I just haven't called them that yet. So I'm going to use an AND gate as an example, okay? And so let's take the AND gate. This is already in and of itself a block diagram, right? Because this is just a pretty picture that is easy to draw and is abstracted from reality. This is not what is happening inside those little black chips, right? The integrated circuits that I've given you in labs. This is not what's inside of those, right? It's something else that we will talk about. And even this could be more specific, right? Because technically this needs a power and ground to tell it what voltages are 0 and what voltages are 1. Well, besides that, what happens when I want a 4-input AND gate? How do I build a 4-input AND gate?
Draw 2 more lines.
Yeah, I draw 2 more lines, right? But let's say that I gave you an IC package of only 2-input AND gates, right? Because that's a possibility, because we have these blocks of chips, and I'm going to do this with actual NAND gates to you in the next lab, where this one, so this is pin 1, right? The top left, and they have that physical indent to orient you on where it is. And that's pin 1, and it counts down to pin 1, 2, 3, 4, 5 in this case, 6, 7, 8, 9, 10. And in the last one we used, this was VCC, and that was ground, right? So that it knows what they are and it corresponds to those. And inside of them, maybe it's an AND gate, right? And then over here, I have another AND gate, and then I have a weird number of pins. And right now I can go build these. I'm going to redraw this real quick because I do want a third AND gate on it. Okay, there we go. You will see weird packages like this sometimes. This one's weird, right? Because there's one extra floating pin. It's fine, it's not a problem. Now, what's interesting about the 2 input AND gates is I need to draw 2 more lines. But let's say I've given you this package and I want you to build me a 4 input AND gate. Well, the way we do this is okay, now I have an AND gate with A, B. So this is signal. I'm going to start with Q such that Q is equal to A and B, and R is equal to C and D. Okay, these are AND gates, and it turns out P, Q, R, that makes this S. Well, S is now Q and R. Right? And I can do that substitution that we've been working on. So that is now equal to A and B and C and D, which is equal to A and B and C and D. Ta-da! I have built a 4 input AND gate. Right? Because what's happened, if we look at this, is if there's a 0 here, that means that has to be 0, which means the output can never be 1 because I need a 1 at both inputs. Same thing happens here. If I put a 0 on either one of these, that makes this 0. The output is never 1. Therefore, we have 8 lines, right? Because I have 16 lines of my truth table because it's 2 to the 4. And that means of all of my 16 lines, only the last one where A and B and C and D are all 1 gets a 1. I built a 4 input AND gate, which you've seen me draw before as this. So when I call this a 4 input AND gate, I mean this, okay? And this is why when I say, right, intermediate signal, Q, R, I will also call them internal signals because they are inside of this. They don't leave. The outside world does not know that Q and R exist because they don't need to, right? So they're a local connection. So if I had within the circuit something else called Q, it must be connected. But when I go to a higher level of abstraction, it doesn't need to know it's there, okay? Similarly, these guys, this A is this signal A, okay? But to the outside world, this guy's not a signal. He's inside the package. He is what's called a port. Okay, it's a port. And so these ports are how I access these blocks. I haven't really used much in the way of ports, right? Normally I just call it a signal and I plug it in and I'll let you guys make the assumption. But these ports are really important because, well, they're going to come around and bite you in the butt if we don't understand them now. But I'd like you to understand how we're building these things as blocks, okay? Because this block building is really important because I don't want to draw that every time I have a 4 input AND gate. Just like I don't want to draw the circuit representation of how we build an AND gate. I want to abstract it, but I need you to understand what's happening. So if I take another one and I want to build an 8-input AND gate, then what I do is I use another one of those, right? And it's just like I grabbed another one of these out of the bin, right? We have a little bin full of electronics. You guys go and grab one of those. You throw it down on your breadboard. You hook up, well, this signal, that signal, and then the output here goes and plugs into, well, I'm going to wrap it around and plug into that AND gate. And then this AND gate I'm going to use and plug its input here. And now I've called this signal A, B, C, D, and then this is my output S. Okay, so if I could package that up into another package, I built a block, right? And it has these ports A, B, C, D, and S that I can plug into really easily. That's what I'm drawing, is I've just pulled another one of these out of my bin. This is a new component, okay? And these components have names, which is, well, this is gonna be AND4 or something, okay? Well, that's what we'll call this. They are named AND4. Now, you might wonder why I don't do like 4 and the reason is simple is because in the future, when I teach you some of our hardware description language, is it really hates having numbers as the first character in a name, and you'll find that's true for a lot of things in engineering, and so I'm going to put the 4 at the end. That's why it's weirdly, the weird convention is there's a purpose, but this guy is named AND4. But then I also need a designator that says which AND4 is this, and I'm going to call this one U0 and this one U1. Why U? I don't know. That's what we've used for component designators for as long as I've been alive. I don't know where the U comes from. It's what it does. Okay. So we're going to go from U0 to U, however many of these 4 input AND gates we need. I don't need another one, right, to make an 8 input because I already have 8 inputs. I can call that L for now. The output L, just put it right in the middle of the alphabet. Okay, now I have an 8 input AND gate, which I could draw as an 8 input AND gate, right? It's our one big AND gate with 8 inputs, and it's really big, but it's still just a block that represents this abstraction. This is what we call hierarchical design because it's a hierarchy, right? It has a bunch of little blocks that build a bigger block that build a bigger block. That's all we're doing. But something I want to point out so that when I draw pictures up here and why I mentioned the word port is simple, is I'm allowed to go like this. So now I have the signal A plugged into signal A, right? That's fine. Sorry, signal A plugged into port A, which connects this signal A to that signal A. They are equal, but they're not the same thing. And to illustrate that, I can also call these an H, okay? So this signal E is plugged into that port A, which is connected to that port A on one of the other devices, okay? So the signal names can be different than the port names, and that's fine. And this A is not connected to that A because one of them is a signal, one of them is a port, okay? Do I need to re-say this or does this make sense? Okay, we're good? Awesome. So then I can draw a big one, I have a bigger block, and I could then stick 2 of those together and I have a 16 input, right? That's all we're going to do. We're going to do this with lots of things. In fact, on the homework, I think I asked you to do the same thing with an OR gate, and it really is very similar, right? And you can just prove yourself with these internal signals. And I want to prove, well, not prove, but I want to really illustrate. If I call this Q, that's fine because this Q is internal to the 4 input gate. It doesn't know that there's an outside Q. However, if I called it A, I have a problem because this A and that A are the same level, right? They're the same part. And that means this A and that A are now connected because they have the same name. Yes.
So if I'm understanding this correctly, like F, that's gonna go to B on the left side, right?
Yes,
Okay.
B on the left side of the second one of these. Right, yeah.
Now, just go back to that U bit. You know, that the U unit is part
Oh.
of an assembly,
Is that what it is? Unit.
Yeah.
All right,
a unit in an assembly.
that makes
You know,
sense.
look at it in discrete fashion and not in.
Okay, yeah, there, before my time.
Yeah. I know.
It's fine not to know things, right? Okay. That's really the main push of block diagrams that I want to get through so that we have just some common vocabulary on that. And we understand, right, that we can wire them up to build bigger and bigger things. And we can imagine that we build a really complicated circuit that gets really annoying. And I don't want to draw a million of these, so I draw a big block. And we're going to do that with more and more advanced components because many of you are going to end up what are called systems engineers. Okay. And what a systems engineer does is, well, they're the counterpart to really the technical engineers, because one of two things is really going to happen to you. There are other options, but these are the two major ones. Is either you go and get a job in industry and you become more and more expert in a narrower and narrower field, right? And you become the guy at, say, L3 or Northrop Grumman or something that everybody goes to if they want to know one very specific thing, and you're the expert, okay? Or you do what I did and you work at small companies and you have to do everything. That's the other option. And you have to learn some of all. The other option is systems engineering. And these don't really get employed by smaller companies. These are mostly at bigger companies. And well, even mid-size really. And what they do is they understand the system. They don't really ever design anything, but they go and draw blocks and they connect them together and they tell someone underneath them to go build it, right? They're technical managers. They have to understand the engineering beneath them. So it's usually an engineer that's been promoted into management. It turns out this pays really well, but it's kind of boring for a lot of people. Not for everyone. We have people that go out and take it and enjoy the job. But for me, I didn't like systems engineering. I was a systems engineer because it paid really good. But what you do is you draw block diagrams and then you give it to someone else and you say, I don't know, this is what it's supposed to do, go build it, right? That's what systems engineers do. That's why block diagrams are important, is we draw these blocks and say something like, well, yeah, these are really bad. There we go. That's a USB block, right? That's all it is. It has a transmitter, it has a receiver, it communicates. Obviously, it has millions of gates in it. I don't have to know how to build it if I'm a systems engineer. I just draw a block that says I need a USB and I give it to you and you go build it for me, right? This is why block diagrams are important, is because this is how we communicate large projects. Oh my goodness, I skipped something. I'm sorry. I have to double back. That's block diagrams. I just want to introduce it here and kind of talk about the ideas of ports and signals so that when it comes back around, it feels familiar, right? I'm going to trick you guys into thinking you already know all of the that know about this, because when I talk about it, you're like, oh yeah, I've already heard that. That's all I'm doing, is I'm priming your brain for something that seems to be really hard to learn. So, as I said, I need to double back because I forgot to do one more thing. Because it flows really well if I had done this right. So let's say I have a sum of product circuit, right? We already know that these are easy to build as our product of sums. But let's say I have you design this circuit, whatever it was, right? Maybe this was the circuit that keeps the doors from killing the world if they forget to open, right? Or they open when they shouldn't. But the only thing you have in your bin, as is the case in our lab, are NAND gates, right? This is what's going to happen next week, is you're going to give only NAND gates. Well, that means I need to figure out a way to turn this circuit into something that I can build with NAND gates. And the nice thing is NAND gates and NOR gates, NAND and NOR, are what we call universal gates. Meaning I can build any logic expression out of just NAND or just NOR. It's really easy, in fact, right? We've seen that as anything that I can put on a truth table, I can build a sum of product as long as I can find a clever way to turn a sum of product circuit into strictly NAND or strictly NOR. Well, let's do it because this is really easy, okay? What's going to happen is we're going to exploit the concept that a NAND gate looks like that or like that, right? You remember the equivalent gates from last time? Either one is fine. You can prove it to yourself if you need to. Draw an OR gate. Oops. Stick inverters at the input, right? Because that's all those bubbles stand for, is they're just inverters. And then see if the truth table for a NAND gate and this gate are the same thing, right? And we would do that because this is now not A and not B. And then we just say it's true if and only if not A and not B are both true. Well, what happens is it's saying or operation of A is 0 or B is 0, right? So A is 0 or B is 0. We get that. That is a NAND gate, right? It's the opposite. This is NAND because AND looks like this, right? So if I take an AND gate and throw an inverter, it moves back and forth. So we're going to exploit this property, the fact that these two are the same, and we're going to combine that with the fact that if I stick two inverters and I put a signal A into it, this becomes not A and that becomes A again, right? And they just switch back and forth, A, not A, A. So two inverters are the same thing. And let's go ahead and start turning things into NAND gates. What I'm going to do is I like to do this conversion right to left. There's actually a way to do left to right. I find the right to left easier. And when you do right to left, SOP becomes NAND, and product of sum, which I don't abbreviate for obvious reasons, becomes NOR. Okay, that's the rule. What that means is, well, let's put a bubble here, right? Well, this is NAND gate. I'm done. Well, not quite, right? Because I've now changed the equation. I've changed the expression. But if I put another bubble right there, double bubble, is nothing's changed, right? Well, if I take these and pull them off, then it looks like so, and we're almost there because this is now strictly a NAND gate, and now I have to do something with this, right? But we've already established that I don't need to draw the inverter. I can just put a bubble on the output of a NAND gate. So let's keep pushing the bubble. Now those are NAND gates. And that's a NAND gate. And because I invert here at the output and invert at the input, I've done a double inversion. Nothing has changed. A is still A. This is a strictly NAND gate circuit. We call this bubble pushing. It's a super fancy name, right? The same thing works for NOR gates, which I'll let you guys do on your own, which is if the output is a NAND or an AND gate and I put bubbles at the input of it, it becomes a NOR, and then I push those bubbles back and they run into OR gates, and those are NOR, right? So product of sum and sum of product are really easy to convert into universal gates. This is what's part of nice about designing it using min terms and max terms, is you get to choose, and this is another perfect example of why you might use min term or max term, is because it will help you decide what my gate's going to become. Now I can do it left to right and like invert these and then add an inverter to A, right? But then I have to add inverters. And the rule of thumb, anytime you're talking digital circuits, is that inverters are kind of free almost. And that's not true when you're building them on a breadboard, right? Because, well, they're complicated and you have to add this inverters. But if you're designing them with the hardware description language, as we'll do in the second half of this class, it turns inverters are free. They don't really cost anything as terms of resources. And we'll explain why in 3610. Actually, I don't think you learn why in this class. But use this bubble pushing method if I ask you to it. We can do conversions on more complex circuits. I don't think I'm going to teach it or ask it this semester. I have in the past. I just don't think it adds a lot because you wouldn't really do it, right? Because we can design better circuits than that. Okay.
All we really did was just switch the OR to a NOR and two ANDs.
Yeah, but think about it as bubble pushing, because I might give you like 2-layer circuits, because those do happen, and all you're going to do is just push. And what's nice is,
So you start the far right, as you can go, and you just put 2 bubbles.
yeah, and the input of the far right gate. And what's kind of nice, and someone actually, I can't remember which of you did it, but one of you asked a question that really got at this, because what happens is if I have an inverter on the output, it turns out I can just push it through and flip the gate. That's what the rule says. So I take the inverter here and push it through and change from OR to an AND, and they're equivalent. Right, that's all this is saying. And so you can do a thing where I could push these through and make that a NOR, and then push these through, and then, well, then it looks like an OR with inverters, and then I would detach those inverters and I would have a NOR circuit.
Okay, so this one on the far right, that's a NOR, not a NAND.
This is NAND.
So if you push to the, so if we push it to the right and change to an AND.
Well, it takes 2 steps to do that. So step 1 is I flip the gate and push it through. So we're still NAND. It was an AND, it is an AND. And then detach it. And now now I can easily turn this bubble pushing again into NOR.
Yeah.
This is kind of beyond what you need to know, because I'm just going to have you design sum of product or product of sum. Sorry, yeah.
Wouldn't that make it universal for chips if you have another connection between the pushing and then another output, and then you could do away with the NAND at the end of it?
Yeah, you could. I'm
So
not
you
going
use
to.
it for 2 purposes.
Yes, you can. Don't worry too much about this in general, right? That's more complicated because we're just going to build good circuits from the start, and we don't have to confuse ourselves too much, right? We'll just make intelligent decisions whether we're using min terms or max terms, and then we don't have to do anything sophisticated. And we can do analysis, right? What's nice is even if you were handed someone else's circuit and you were told to fix this, right? We have the circuit. It was built 40 years ago. We don't know why it doesn't work. Figure it out, right? All I would do in that case is I would write down the expression using like a truth table through the intermediate signals. And then I would using my analysis techniques, right, writing those down. And then I would redesign it using min terms or max terms.
Probably it didn't work because they were vacuum tubes.
Yeah, that's true. Okay. The other thing that I need to point out is it's really easy. Like I say they're universal gates, and I keep talking about inverters and drawing inverters, and I say you only need NAND, right? It turns out it's really easy to turn NAND gates into inverters, because if we go look at the NAND operation, right, it's saying that it's 1 unless both of them are 1. So it's just a matter of connecting the inputs in intelligent ways. And so let's say I take this inverter, but I don't have inverters. Let's say I broke my little inverter IC chip, okay? And I have a spare NAND gate chip lying around. Well, what happens if I do this? Where this is just a single wire A. That means that ports A and B internally, right, are connected. They're always the same, which means these rows can't happen, right? That's physically impossible. It is either 0, 0 or 1, 1. And if it's 0, 0, so if the input A is 0, I get a 1. And if it's 1, I get a 0. I build an inverter, right? So as a matter of practice and protocol, if I ask you to do something like design this circuit using universal gates and you just draw an inverter, you don't have to draw this NAND because it's really easy to make inverters out of NAND gates. The same is true for NOR. It's probably going to be a homework question, but right, the proof is easy. It's just truth tables. Okay, sorry, I had to double back on that one, but I can start pushing forward to the next topic. Okay, so what I've done for you so far, right, is we've talked about these design tools and analysis tools and ways to evaluate things, but there's one thing that we haven't really done yet, which is how do we describe what happens to a circuit in time? How do we show what happens over time? How do we show what happens as the circuit changes? Well, it's convenient. We just call it a timing diagram, okay? And these are going to be really terrible drawings. I apologize because timing diagrams are hard to draw. Unfortunately for you, anytime I give like exams, I will provide you with these printed out. And all a timing diagram does, all right, I'm going to stop talking for a second so I can actually draw good lines a little bit. Okay. So let's say I have a circuit, and that circuit is this. Okay, it's not a product of sum or sum of products, doesn't really matter, right? You guys still know how to analyze this. And we simply go ahead and look at the intermediate signals and we say, well, what is D? Well, D, there's an AND gate here, so it's going to be A and B, but it's NAND, so it's not that, right? It's not A and B. And I said this before, and I'm going to say it again because it's really important. It does not equal not A and not B. There's a difference between not A and B and not A and not B, okay? So if I were to write that out, right, there's this implied parentheses underneath the not bar, okay? And that parentheses is unbreakable. You're not allowed to factor out of it until we learn something later in this class of how we would separate these out, okay? And so this is not A and B. E is much easier, right? We've seen this B or C when Z is, well, the and of D and E, which then I can substitute in. Now this describes the circuit, but let's say we want to analyze the circuit as it changes through time. Well, that's where these timing diagrams come in. And the way timing diagrams work is I'm going to call each of these rows A, B, and C, my input signals. And we need to understand that this is a 0 and the dashed line is a 1. One being on, high, right? If we're talking about the TTL level chips, it's 5 volts. If we're talking like low voltage CMOS, it might be 1 volt, for example, nowadays. But we use 0 and 1 as off and on, okay? And now, just like the truth table, where I wrote down 0, 1, 0, 1, 0, 1 for the rightmost column, and 0, 0, 1, 1, right? It alternates. I'm going to do the same thing here graphically through time, where the x-axis is time. And what that's going to say is A is going to start 0, 1, 0, 1. And I need to make that change. Well, I have 3 variables, so I need to have 8 times of change 0, 1, 2, 3, 4, 5, 6, 7, 8. And then I need B to change half as often as A did, right? And so what I'm going to do is I'm going to take another color and make things messy, because I want to be fairly precise in this. And what I'm going to do is, to help my drawing be fairly consistent, is I'm going to mark out what I call the important points, which is where things, well, I don't really need this last one, where things change, right? If an input doesn't change, the output can't change, right? So this is just going to help me when I get down here. As I said, B is going to change half as often. And I'm going to, well, I'll do it this way. I'll talk about that later. And then C changes half as often as B. And now I can look vertically. And this first column is 0, 0, 0. The second column is 0, 1, 0. Oh, sorry, the second column is 1, 0, 0. 0, 1, 0. Now, there's something kind of obnoxious about this, which is, let's go ahead and write these out. What's a good color? I guess we'll go back to black. 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0. You'll notice that the binary counting, if you paid attention to the columns, goes up from C when I did it this way. 0, 0, 0, 0, 0, 1, right? So just be aware that it's kind of, when I did it this way, it's the reverse of what you might expect in the truth table, unless I draw the truth table. Well, C is changing the least often, so that's what this truth table is approximating. Okay, does everyone see why? All right, it's just something to be aware of, because again, as long as we keep things straight, it doesn't matter, right? The order doesn't matter as long as we're careful. Well, let's look at our circuit, and let's go ahead, A, B, C, and I called it D. Let's call it D, and go look, what is D? D is not A and B. So when is it not A and B? Well, it turns out it's kind of easier to think about this A and B and then just kind of flip it the other way. But let's do E first, because it's a little bit easier, okay? E is going to be easier to visualize. I should have labeled those the other way, but it's all right. Okay, so E is going to be true if B or C is true. So what I do is look at B and C only, because A doesn't matter in this case, and I say B is true in these 2 columns. There's my 1. C is true in all of these columns after this point. See why I did the vertical lines? It's because it's helping me keep track, and I just continue on. Well, down here, neither of them are true. Neither B nor C is true. That's what my E looks like. That one was easy, right? Or is easy, is I just look for where either B or C is true. Now let's go do the A and B. Well, not A and B. If I was doing A and B, what I would do is I would say, where is both A and B true? Well, I really need another color. This is unfortunate. What we're going to have happen is here, A and B are true. Okay. I'm going to put a dot there. A is true, but B is not, right? B is, but A is not. Both of them are. I think that's all of them, right? There's only 2 spots. Well, what that means is if it was ANDed, then those would be true. But because it's NAND, it's the opposite. That's false. That's false. And everything else is true. Now, I was 1 line short. And all I have to do here is, well, what I call the output Z. Well, Z is a function of A, B, and C, right? But it doesn't care anymore. I've decoupled it because I've written these intermediate signals, and the only thing I have to look at is D and E. Well, more specifically, is it D and E? It is. The function Z is D and E because it's going through an AND gate. And now I just look at D and E. I do that operation, and anywhere that they are both true, here, it's going to be true. So starting here and ending there. Oh, oops, sorry, I'm off by a level. Doing this reverse. Yeah. Oh, I got one more, right? 1 and 1. So I've got a little blip. 1 drops down, 0.
No, D goes all the way across. D1, D and E.
D and E. D has a 0 here. So this is 0.
Yeah, but then on the end, it should go all the way to the end
D drops to 0.
No, but see where D is 1, the input 1, it goes all the way across. So shouldn't that be true all the way across?
You mean in the beginning?
Yeah. On the,
No, because E is 0.
oh, okay. Yeah.
So if either of them are 0, it's going to be
Yeah,
false. So we got 0, 1, and then we dropped out to 0 because of this divot. And then go back positive and back down.
Yeah.
Yeah. Good question though. Any other, does everyone follow that? So the first thing that you'll have to do, the first homework question that I posted on timing diagrams in your homework is you're going to do a timing diagram for an inverter and nothing else, right? That's going to be pretty easy. We'll start simple and you're going to build up. Now, the reason that timing diagrams are important is, well, it allows me to see how things change through time is a big one. And the other one is you're going to spend a huge chunk of, well, your lives, to be honest, if you become a digital engineer, staring at these things that are generated by computers. Because what happens is when I need to test something, right? If I'm going to test, that's what this is doing. I'm just testing. Does the circuit do what I want? You're going to tell the computer what the inputs do, and it's going to tell you what happens to the outputs. And it's going to create a diagram that's a timing diagram, and you're going to see if it makes sense, if it's doing what it's supposed to. This is why timing diagrams are ultimately important, but it also gives us an interesting way to talk about the circuits changing through time. So do expect to see these on homeworks and exams, and I'm going to ask you them in general, like on an exam, I will provide you the A, B, and C. So you don't have to worry about that, but get familiar that all I'm doing is enumerating all possible input combinations, right? And I don't need to do more than 8 because anything more than 8 is repeating for 3 inputs. If I have 4 inputs, then I need twice as many. I need 16 lines, and that's annoying, and I'm not going to do that to you on an exam. Okay. I've posted again a video that talks about timing diagrams. It's linked through an announcement. So if you need a refresher, it's there. I'm sure there's tons of resources online that actually talk about timing diagrams. And that's one of those things that I think is actually taught well online. So not everything is taught well online, but these are. We'll come back. We'll do another one if I end up with time at the end of this, just so we get more practice in. I think we will. I think we'll have time to come back and refresh. We'll see them again. I'll talk about them again. But let me look at this. This is kind of an interesting one. I'll confess straight up front because I teach 2 sections of this class. Okay, one of them is in the day, one of them is night. You guys get me for 3 hours in a row, and they get me in 1 and 15-minute chunks. So they get less tired of me, I assume. But it also means that I think about things weirdly sometimes for you guys. So if you get confused, let me know. Like if I skip something, you're like, what just happened? Let me know. Because like the first thing, these are my lecture notes. I'm actually thinking about posting these online. It's a double-edged sword in that it will provide you with information of where I'm coming from. But I'm also going to look like a bit of a madman when you see this because I'm a little disjointed in my thoughts sometimes. And so I'm not sure how helpful they will be. I don't want it to be a trap, but I do want to be helpful. So I'm debating still is what I'm getting at is I'm not sure if I'll post them. So getting on with it. I am going to start back and I'm going to do a complicated analysis question, okay? Because analysis is really important because understanding what these circuits are doing, and that's what I have on the list is let's go analyze a circuit to make sure that we know how. There's the homework that I posted, homework 2. I hope you all turned in, did homework 1 right. I don't want you to fall behind. I hope you guys do them early. Like I would recommend like tomorrow, if you can, go and start homework 2, because you're gonna know all you need to do to start that. And if you run into something that you don't know yet, I would be very shocked. Actually, I think you're gonna be well covered by the end of this. In fact, right now, I think you could do most of it. But get a jump on it because it buys you time later in the semester, right? If you're ahead of things. And right now is like the smallest homework that you're gonna have. So like if you're in 1270, I know Dr. Jackson assigned like 4 homework problems for his first homework, right? And they're gonna get bigger. My homework 2 looks big. It's not. I just make you guys do a bunch of analysis and a bunch of different things that are all very similar and it should go pretty quickly, but it's just to make sure you guys get comfortable and allows me to see if we're actually confused and no one's willing to admit it. Because that happens. So give me a minute while I draw a really complicated circuit up here. Start right. Goes through the inverters in there. It's also here. Goes into this AND gate. Y there. And then Z. Okay, I think I drew it right. So this will do 2 things. One, it will be kind of a nice introduction. So the first thing that you see, the first time that you see a really complicated circuit won't be on your own, right? And then we'll talk about like weird things that happen in circuits. Oh, I think there might be one. Nope, that's fine. All right. So all of this is just going to be, let's step through and analyze it, right? This looks like a really big mess to find F. But we're just going to do this one step at a time so that we keep it simple, okay? The trick is always don't overcomplicate it. If you want, right, we could easily write this is not X. That's the first one. It's easy. In fact, you could probably skip that one once you've done analysis a couple of times. Doesn't even take a bunch. And then we have an OR gate, and we just have to follow it back. So it's Y or not X. And in fact, I probably should write that the other way because it drives me crazy. Oh my goodness. Not X or Y. And I need to call this not F, I think, because it's going to get in my way. And so I'm going to just step outside of the alphabet and call it alpha. Okay. Because I don't want to run into F when I start doing intermediate signals, because I'm going to call this A. And now I'm going to call this B. Well, I already know that this node is A and B. I don't even know what A is yet, or B is yet, right? But I know that that output is A and B. Let's go find B. Well, B has a problem because it has another unknown that I'm going to call C. Okay. My only point here is it does not matter what order you go in to label your intermediate nodes, as long as you recognize the connection between the intermediate variables and the input variables. Okay. So what is C? Well, C is finally easy because it's X and not Z. Great. I didn't give this guy a variable name because he's easy and trivial, and I think it would just take up time. This node here is just X still. You could write that down if it helps you keep track, right? It's just X, we have to follow it through. This one, however, see, we're on D. What is D? Well, D is the not of Y and Z. So Y and Z knotted, Nand, right? Remembering it is different than not Y and not Z. This is not Y and Z. Okay, then the output here is the X. This is going to be kind of funny. So D, this makes that E. And well, E is the AND of X and D. Totally fine. 2 makes an input variable and an intermediate signal, right? Because they are related. I'm going to do a substitution later. Make sure that you don't accidentally double up these new variables, right? That would get really confusing if I accidentally called this B or something and I had a B there and then I do substitutions. I don't know what's going to happen. And now we can ask the question, am I ready for my output gate? Well, my output gate is alpha equals, I didn't even give this a name, so that's okay. A and B or E. Okay, well, that's not our input variables. Let's go substitute what is A. Well, A is not X or Y. And B. So I need these parentheses, right? Because if I don't, it doesn't follow the algebraic rules. I need to make sure that these terms are grouped together. You're better off adding more parentheses than fewer, because if you had something like F is equal to A and B and G is equal to C and D, and then I wanted H to equal F and G, and I kept the parentheses, then I would say that is equal to A and B and C and D, right? I've used extra parentheses, but it doesn't change the meaning of it because parentheses act like multiplication of what's inside. I hope we don't algebra at this point, because if we don't, we're in trouble, I think. Right. Anyways, I'll erase that so we don't get confused with these floating variables. I just want to illustrate it. The parentheses are good so that when I go and substitute B, what is B? Oh, I never wrote B, my bad. It is the not or, I'm gonna have to scoot this over. the not or of C or Y. Agree? Okay, keeping in mind the kind of unforgiving not term, meaning there's this kind of hard parentheses there, it still exists. So I'm gonna have a hard time separating that out later. That's okay. Now when I say B, B is not C or Y. Okay, so I've got the A and B, that's taken care of because of the multiplication. And then I say or E, I follow to E, which is X and D. I'm not done yet because I have C and D in here, right? I need to get all the way back to my beginning. Sorry, I'm just gonna write this out, then I'll talk through it. Well, that's fine. So C is gonna be X or not Z. Sorry, X and not Z, that'd be really bad to mess up. Or Y, Y is okay to use. And there's a big not over that whole thing, right? And then I need to go the or X and D, X, and I'm going to use parentheses to make sure that D stays intact regardless of what D is. Well, D is not Y and Z. Okay, this is what I'm going to have you do on the homework, right, to make sure that you can do this yourself because it's different from watching me do it. But does this make sense so far? Okay. Now, we can say that this is a mess of a circuit, right? And if I gave you this circuit, this equation, theoretically, you could build this circuit off of it. The design part is harder, and the hardest part of this is recognizing the or part, which is why I'm going to have you do a lot of design and analysis practices, because you can recognize that this anding is ORed, so I have an output OR gate, right? It's hard to do an AND gate as your final gate. If you tried to draw this out, in fact, it's fine to do, right? If you're not sure and you wrote the AND, you start building that and you'd get really confused really quickly of how to build the rest of the circuit and go, oh, okay, it has to be an OR. So it's okay to try, right? I like to say, because it's true, getting it wrong is the first step to getting it right. It's just part of the process. Anyways, this is a really complicated analysis type question, right? This is really as complex as I'm going to get on you. I'd be astonished if you ended up with anything more complicated this in industry, right? Because the time that you'd have to do this in industry, and I've actually had to do something kind of similar where I'm giving a horrible circuit that I don't know why anybody designed it that way and figure out what it's actually doing with its inputs. You'll do it using a tool. It's called a PLC, which is a programmable logic controller. Tons of our graduates go and work with PLCs, and they are programmed with horrifying logic all of the time. And you have to figure out, in fact, we've had senior projects, multiple recently, that are basically fix the PLCs for Northrop Grumman or something similar, because they have really old material, because they're a government contractor, which means they don't like to spend money that they don't have to. So they have critical infrastructure running on 30-year-old technology.
Yeah,
Right.
I did that in the service, ladder logic.
Yeah, doesn't surprise me. It's really common. Okay, so that allows me to introduce the concept of Boolean algebra, right? I keep talking about these as Boolean expressions and we write them like algebra. Let's talk about the rules of algebra, okay? If you're really strong in algebra, this section is actually going to be really easy. If you're weak in algebra, this might be a little bit miserable, and I'm sorry, because we're gonna just talk about the rules for Boolean algebra. The first rules being, we do not have subtraction, we do not have division, and we cannot square things. So B times B is BB, okay? That's annoying, it's obnoxious, but it's the way it is. So I'm gonna keep this board for just a bit, but I need to bring this a little bit better into the light for the video. And I need to erase some things. Because what I want to do is I'm going to keep this mess of a circuit up here, this messy expression. And we're going to talk about how we simplify circuits. How do we identify what's wrong with them? And then we're coming back and we're going to make this smaller, I hope. I think this simplifies. I'm not 100% sure. I haven't tested it yet. It should, right? This is a really ugly circuit and it's very weirdly designed. So most of the time that means it's going to simplify. Okay, so what do I mean by simplify? How do we make simplifications easier? Well, let's say that I have a circuit that's described like so, right? This has an AND gate as the final out gate, and then one put of the AND gate is B, and the other AND put is A or B. And this is an important question, don't be embarrassed, but does anyone think that they couldn't design this circuit? Because I will do it if someone thinks that they can't do that. And really, don't be embarrassed, guys. If anybody judges someone for not knowing something, I'm going to be angry because you're allowed. This is weird. It's different. It's new, right? I know things all the time. I'm sort of someone here with lots of experience in digital logic and PLC is going to be correcting me throughout. I'm fine being wrong, right? It's okay. My only point is make sure you can design this. It's going to be in your homework, so you're going to make sure you can. But it's important, okay? So now, what happens to this? This is algebra. So let's talk about what property can I use here? Do we remember our properties from algebra? Distributive, right? I can distribute the B across. I can multiply it by both of those terms and end up with AB or BB. Well, what is BB? What is B and B?
It's just B.
It's just B, right? We've done this before. What happened when I plugged the NAND gate in? Well, it simplifies down, and you can do the truth table for this, right? You could draw the AND gate of B and B, but you look at this, and well, there's a rule that says the same thing added with the same thing is itself, A, B, or B. Well, we can build on that, and what happens if I have a circuit that is B or not B?
So in the case of the first one, would distributing it simplify it at all? Because you're still using, because in the first one you use one AND and one OR gate. But then when we simplify it, we basically do the same thing, right?
Yeah, as far as complexity goes, it's actually very similar.
Okay. That's
but
just an example.
Eventually we will end up in situations where this would actually make a much simpler circuit. Yes,
So in that first one, wouldn't it flip what your final gate is to an OR gate instead of an AND?
it does. Yes, it changes. And you may have to deal with the ramifications of that when you design, or it may be really simple. And because you can go the reverse, actually, if you wanted to reverse this, and this is kind of fun, because you can factor things out, okay, which becomes B, and this is actually another rule, because what you're seeing, I'm sure I heard someone say something kind of under their breath out of confusion, and this is kind of any fun. So let's factor out the B. B times A, or, well, what is the factor out of B? 1. B or 1. Right? Okay. Let's just A and B. Right? Because A or 1, it's always true. Right? If it's A or always true, it's always true. So guess what? This whole term is 1, making the expression B. Now, we can see this before, right? Let's look here, A and B or B. Well, let's think about that in terms of the Venn diagram, right? This is one of your tools, A, B. I have the term A and B, or B. Do I need that red squiggle to fill in the same amount of area? It doesn't add anything, right?
Oh, so this does. Okay.
So it simplifies down to B. I wasn't quite ready to talk about that one, but it turns out my example put it that way, right? So A or 1 is always A. right? Or sorry, A or 1 is 1. It's always just 1. I got ahead of myself because the next step, let's ignore this for just a second, which is, let's use X, right? Because I don't want you to think this is everything. I'm not always A, right? I want to keep in mind that these are variables and they can be anything. And if I have, well, this is A or 1. What about X and 0? Always 0. It can't be true because I'm putting a false on one of the inputs. It breaks. So X and 0 is always 0. X and 1 is just X, right? I've just tied one of them to true, and now it just depends on X. Right? Those make sense. Those are easy. This is where the Venn diagram can come in helpful sometimes if you need to think about these simplifications. Well, let's go to the next example that I was going to do because this one is kind of fun. B or not B. When is that going to be true?
Always? Or is there also an A that, like, are you implying?
There's no
A?
implied
Oh,
anything.
then just always.
Always, right?
Always.
Because if B is 1, it's true. If B is 0, then not B is true. So I can't be false. So B or not B is 1. Yeah, is the question. Similarly, I can have something that is F and not F, which is never true, right? Because if F is 1, then not F is 0, and I can never have both of the inputs be F. And keep in mind, these are real circuits. And this is why I've changed things around this semester. So if you're resenting me for being weird, here's kind of why, is because we can go draw this circuit. Right, that's your circuit. And because it inverts, we can see that those both inputs are never going to both be 1, right? Yeah.
So since B and not B goes to 1, does that mean you can replace?
B or not B.
Yeah.
Yeah.
Yeah, so does that mean you can replace the 1 in like the B and the A plus 1, A or 1 with the B or?
Sorry, where are we pointing over to this column?
Yes,
Which row?
at the bottom.
This one.
The up one. Yes, that one. So can you substitute the 1 in with the B or not B?
Substitute the 1 in with the B or not B.
Yeah, because,
Oh, yeah, I could put a B or not B into that.
okay.
In fact, I could put an S or not S if I wanted, right? I can introduce whole new variables. And in fact, the worst thing that I'm going to do to you in Boolean algebra is I'm going to give you examples of where you actually have to make it more complicated to make it less complicated. Don't worry, I'll do a very small amount of that and I'll make it kind of obvious, I hope. But I'll keep it light. Don't worry, I won't do too much of the pain. That was like half of the class when I took this equivalent, and I hated it, but it is kind of fun. I'm sorry. If you don't think algebra is fun, I'm sorry. This major might frustrate you, or you're going to come to love algebra, because I didn't love algebra until I finished the degree, and I look back and I was like, that was kind of fun. I miss it. And what you're going to find is that we're going to teach you all this really complicated math, right? You're going to take Calc 1, 2, 3, differential equations, linear algebra, and it turns out that everything is just algebra.
Yeah.
Yeah. And so, in fact, what we're going to teach you in all those classes is how to turn everything that is complicated into algebra. Question?
I'm still stuck on how B and B still is B.
B or this one,
No.
or B and B.
Yeah. how
Oh,
B.
that's fair. Yeah. Let's look at the truth table, which is I don't remember what I call that. Okay, so in the AND gate, we're doing AND, right? So this is the truth table for AND. But B and B means this becomes B. So these are equal. B equals B, which means that this whole row, those two can't be true because I can never make the inputs be different.
Right.
So that means that the output of this is 0 if A and B, meaning B is 0, and it is 1 if B and B is 1. So what it's saying is the left side of the truth column, truth table, is 1s. That's 1. So therefore, right, the right side of this is B, because that's what I said B was. And so now I look and see that the right is equal to the left. Because these middle ones can't happen.
Thank you. That makes
Yeah.
sense.
No problem. I'm sure you weren't the only one. Okay, let me go pull up. So for reference, you guys in your book in chapter 4, which I'll go ahead and post, and if I forget, send me an email, because I know not everyone has their books yet because the bookstore is terrible. I shouldn't say that on video, but we've been really frustrated this year because, right, I can say that because half of you or a quarter of you don't have your books yet, which is really frustrating because they're helpful. Even though I've detoured a little bit from them, right, it's still helpful. But the most important thing is in chapter 4 of your text, there is a table. It's table or figure 4-8 according to what I've written down. And it's going to have a whole list of these Boolean algebra rules, properties that you're going to be able to use to simplify complicated things. Okay. All right. I don't feel bad erasing them because there's a table that'll tell you, and I will post it. And you can like look them up online. I'm certain a quick Google search, right, of Boolean algebra theorems or Boolean algebra rules or what is Boolean algebra will find results for you. And this is another one of those things that are actually pretty good examples online if you need more. And it just kind of takes practice to get good at it. Like on math, right? It's just practice. Babies aren't good at math. They just practice it a bunch. Okay, so let's see. What am I missing? Oh, this one, I've mentioned it before. Right? This is the Boolean way of writing it, is not x is x, double inverting x. We have this one, x or x. Well, it doesn't matter. It's equal to x. It's going to list some obvious ones that I'm not going to go through all of them. Right? You can flip the order of addition, just like you can flip the order of multiplication. This is what we call linear, meaning that linear equation really just means the order of things doesn't matter, right? And this is important to understand because like the circuits, if you're taking currently in or will be taking ECE2700, your circuit elements are linear, meaning as far as analysis goes on the output, it doesn't matter if resistor 1 or resistor 2 comes first. Okay, order of your circuit elements doesn't matter because they are linear. This is linear, order doesn't matter. I prefer this one, right? Because I like the alphabetical order because it's easier for me to grade. And if it's easier for me to grade, then I'm going to give you a better grade because I'm happy instead of grumpy, right? Okay. Let's see. I've done the distributive. Yeah. Okay, so I'm going to do one of the more complicated ones. This one isn't in your book, so I want you to pay attention to this one because this one is really good. And it prevents you, if you follow the book, you have to do some really complicated, annoying things to figure out what the simplification is, right? Because what you're going to do is you're going to do a bunch of this Boolean algebra that I'm going to post an assignment for. I haven't yet, but I'm going to. And you're going to start seeing things and being like, I feel like that should simplify. And one of those examples is, sorry, where is it? Well, let me do a different one first because I don't think the book uses this one either. Let's look at this one. What is x and y or x and not y? Well, we can think about this in a couple different ways, which is one of them. We've already learned we can factor, and we can pull out the x. Right? And then we say, well, this is just 1, it's always true, x. X and not x or y is equal to x and y. Why is that true? Well, if I multiply it in, I get x and not x or x and y. X and not x is always 0. So it doesn't help. It doesn't do anything. So we ignore it. Now for the cool one, now that I've gotten those ones out of the way, keep losing my erasers. X or not x and y. Now, this one starts to feel like you should be able to simplify it, all right? But we're like, well, I can't factor out x because I have x and not x, and so I can't factor. But what we can do is we can do a truth table, right? Truth tables tell us what things are supposed to do. So I go draw a truth table, and I say, well, I have x, y. And now you could do 3 columns, right? Do 1 column for x, 1 column for not x and y, and 1 column for the third. Or you can do it kind of the shortcutty way, which is let's just go 1 term at a time and start filling in ones. When is x true? Because it's or, right? So if either of these terms is true, then it's true. The and case is harder to do without multiple columns, but the or case is really easy. So anywhere x is true, this is true, right? And now I just have to say not x or y. Well, that means 0, 1, right? You see that? We see the affiliation between the zeros and the ones and the variables x's and y's. So 0, 1. Well, 0, 1 is here. I have no more terms, so that leaves this to be a 0. What is that? Or it's an OR gate of x or y. So this simplifies to that. See, and so this is a little bit more advanced, right? Being able to write out a truth table and figure out what you built is one of the harder parts of this, but that's all you've done. Now it turns out if you went ahead and elaborated on this, and let's call this z, right? The output's going to be z, and let's start making connections between things. Let's go build it with min terms, right? What is z? Well, z is equal to, and for this room, I'm just going to write this out and then I'll talk through it. Well, sorry, I hate being in the way, but I think I just have to deal with it. Let's look at this min term, right? That min term is not x, y, right? This one is x, not y. And this one is x and y. Okay, so we know that this term must be equal to these, but this is way, way more complicated. Now, here's what's cool. I know, and you will now, that 2 terms in a sum of product or product of sum can simplify if they are what is called logically adjacent. Now, what logic adjacency says is that they differ by only 1 term, or you could think of it as 1 bit. So what that means is, see how 0, 1 and 1, 0, they're both different, both x and y are different in this, but x, y is 1, 1 and 1, 0, that's logically adjacent because only the y term changes. Guess what else? This x, y is also logically adjacent to this min term because it's only different by x. So what that tells me, if we understand that being logically adjacent to something means it will simplify, okay? That's very convenient for us because now I can do the thing that I told you about that is absolutely awful, which is I have to make it more complicated to make it less complicated. But let's use, I think it was you that asked the question, is who asked can I just add B or not B into the equation? Oh, that was you. I was on the right side of the wrong spot. Let's do it. And I need logic adjacency, so X or Y. I just need another one of those, right? This is utilizing the fact that A is equal to A or A. XY is equal to XY or XY, right? I've used one of my theorems in order to make this more complicated so that these two terms are going to play nice together. And those two terms are going to play nice together because they are what is called logically adjacent because they only differ by one term. Why does that mean it can simplify? Well, let's branch it. Let's bring them together, not X, Y, or XY, or X not, oops, X not Y, or XY. And now, see this Y? Just factor out the Y. And over here, see this X? Factor it out. Now what happens? Well,
One.
yeah, exactly. 1 and 1. Not X or X is 1. It goes away. Not Y or Y is 1. It goes away. And I get Y or X. See, now I've just gone in a circle, right? I've hopefully linked this to the truth table, to making min terms, to simplifying, right? That's the full circle. It's just where you start from. That's right. The only riddle is, or do we start from a circuit, make an expression, and then simplify, right? But it's all linked. So instead of doing what I would have last semester and teaching you Boolean algebra, and then 3 weeks later revealing why, I've gone the other way, right? I've taught you to be engineers. Now I've taught you to be better engineers. We can design things and simplify them using nothing but min terms. Now, it's going to come as no surprise when in a week or two, I teach you a better way of doing this, right? Because it feels like if it's this easy, maybe we've got a better way. Well, we do, and I will teach it in a couple of weeks. But first I have to torture you with this.
But both ways will be on the exam.
Yes. Okay. Sorry, I sometimes go quiet for a little while on purpose, just so you guys know, because one, the more I talk, the faster I talk, right? I think that happens to everyone as you kind of start tumbling downhill. And I know some of you, you don't think about this, right? But I'm sure like half of you or more hate public speaking. And you have to realize, right, all of my job is basically public speaking. And so I use tools because one of my deficiencies when I publicly speak is I accelerate. And so I'm going to stop and give you guys time to digest on purpose sometimes. I'm not forgetting that you're here. I'm not that scatterbrained. I'm close, but I'm not quite. Okay. Speaking of scatterbrained, let's just do some examples, right? Because I don't think we're ready for this because that's complicated and annoying. And so let's do some simpler examples. And we're still one rule short, right? I promised you I'd teach you how to get rid of these semi-permanent brackets that I can't get rid of yet. There's a tool for that, and you're going to hate it more than anything else in this class, maybe. But we're not there yet. So let's go ahead and pull an example. Let's do okay. A or B and A or not B. Let's simplify this expression, which is the same way of saying, let's simplify this circuit, right? This is a circuit. It's just a way of expressing a circuit. Well, we could go look up this table that you have. And on your table, if you pulled it out, there's like a list of dual properties, because for every rule that we have that is friendly to sum of products, there's a rule that is friendly to the product of sums. But let's say you're me and you hate product of sums. Let's turn this into sum of products, okay? It also illustrates rules really well because we know how to FOIL, right? Let's FOIL. A and A, or, right, because that's what foiling does, is it adds each of the terms to each other. So A and A, or A and not B, or B times A is A and B times not B. That's that expression. Take 30 seconds to write that down and simplify it. Then I'm going to do it in front of everybody, but take a moment. Go ahead and look up when you're done so that I kind of know. Because I want to give everybody a chance, but I know I'm scary looking, so people like to look down. Okay, it kind of looks like we've got all but a couple. Sorry for those that aren't done. I unfortunately have, more to cover. All right, let's look at things that we know, right? The easy ones. A and A becomes A. B and not B becomes 0. Okay, let's bring everything down. What's our next simplification? What's a good simplification here?
Pull the A out.
Pull the A out. I like that one. A or A. That, right? And then we have B or not B, which is 1. So I can just cross that out. And now I have A or A, which is A. That's cool, right? That whole circuit is trivial, is A.
So whenever you have a 1, can you just drop it? Like if you have 1 or B, you can just drop
Well,
it?
we have to be careful, right? Because there's different rules. 1 and something is something. So 1 and X is X, whereas 1 or X is 1. Yeah. So we have to be careful with the rules as long as we keep them straight, which is just going to take practice to become familiar, right?
Okay, because like what I did is I pulled it out and I said A or 1 plus.
I see what you did. So what he did is he factored the A out of all of them in just one go, okay? Which is allowed, right? It's still algebra, which becomes 1 or B bar or B. And now you have the rule of 1 or anything is just 1. And A and 1 is A. Because one input is always true. Okay. Same principle. Actually, I'm just gonna write this up here. I'm gonna write one up that you guys can do on your own time, like after class if you need practice. Never mind. I'll skip that. I'll come back if there's time. I'm not sure there is. I'm just gonna try and make sure we get through everything. Earlier, I was really confident, and then I got sidetracked somewhere. Let's do this one. All right, so we need to start looking at this and thinking about maybe where can I simplify, because it's fairly complicated, right? Because I can pull out this A of the B or C bar. In fact, I could pull it out and have A, B, or C bar, or B bar, C bar. And it turns out, I think that that one's going to do us pretty good. But it's hard. Does anyone see the difficult to see simplification that I have? There's something that we can simplify up here, but it's more difficult to see than factoring the A. Yeah.
Can you factor not C out of like the A not C and A not B not C?
Yes, you could absolutely factor out that C bar, and that one is probably actually a better one, right? I actually like that simplification better than factoring out the A. Does anyone see a third step that I could start with? That's okay. This is the hard one, but the fun one that I was talking about. Remember that? Where the expression, and this is hard. In fact, I think if I remember right, I chose this one on purpose because of the difficulty of spotting it, where I have the rule that states, sorry, I just lost it. X or not XY is equal to X or Y, right? That was the kind of cool rule that I talked about before. Well, this is why it gets hard, is because now I have to make the affiliation between this and that, right? So what I'm going to do is I'm going to bust out a red, and I'm going to call this X. I'm going to call this A, not X. Can you guys be quiet for a minute? I just want to make sure we pay attention here. All right, then B is Y. Now I've made that association, right? I've assigned them to the variables that are familiar to me. This is much harder to do when I'm using X and Y and this like not X. I have to say not X is equal to X, right? That's annoying, but this is a little bit easier. And I say X is not A. And so what that means is I have X or Y. So X is not A or Y is B. Does everyone see that one? That rule that it helps. Every time I use this, I write it out like this if the variables are anything besides exactly what they are, because this is very easy to mess up. Okay, now I have that, and now I have or A C bar or A B bar C bar, and now I can do the clever suggestion, which is factor out the C bar. And what happens to A or A and B?
You do the A plus B, no?
It's actually easier than that. That would technically almost work. You'd actually be off by a little bit. But what happens is it turns out the A and not B can't happen unless you already have A. So the A and not B is redundant, right? It's more complicated than its simpler cousin. So it just drops and I get not C A. There we go. Well, guess what we have again? Does anyone see it?
So the A's.
Yep.
Turn her one.
Exactly. I have a relationship between those terms. And now I have to call, once again, not A is X. A, then, right, so if not A is X, then A has to be not X. And C bar becomes Y. Did that right, I hope? And then I'm going to come up here so it's easier to see. And I'm just going to associate, we know that it is X or Y, and X is not A, or Y is not C. And we're done with that one. And I just need to pull in or B. And I'm done, right? There's no more compound expressions. There's no hope I have of simplifying that any further. Assuming I didn't make any mistakes along the way, right? Which is why showing your work is really important, because I am a big fan of partial credits, right? I like to see what you guys did. And if you did it right, but you made a simple mistake, I'm going to give you points. I had a professor when I was an undergrad for control systems who, once you made a mistake, if you kept going, you actually missed more points than if you just stopped, because every mistake that you made got worse and worse and worse. So like the worst example of that is one time I had like a 20-point question on the exam and I got minus 13 points on it because I flipped a negative sign one time. And it was like a whole page of derivations. And every time I didn't have that negative sign, he subtracted 1 point and I ended up negative 13. I'm not going to do that to you guys, right? It doesn't help. It doesn't teach you anything. It just makes you feel bad and it makes you hate me, which is not what I want, right? My goal is to make you graduate and become engineers, not to fail you because I'm mean and grumpy. So if you show all of this work, but you did something wrong and you got here, you're going to miss minimal points.
Can you go over how you cancel the A or A and B not?
Yes, absolutely. So again, truth tables are our friends on this one. And so let's go ahead. AB. And now I'm going to, because I have an and term in here, I'm actually going to separate these out. And I'm going to call this A and this A and not B. Okay. And so what's going to happen is, well, the first term is true if, because I'm building up to A or AB bar, right? That's what I'm building up to. Well, A is true here and here. Okay. Where is A and not B true? That's this row and only this row, right? Because that's A and not B. That's one. And now this is an OR of these two columns. Does this column add anything to the ones that I'm putting here? Nothing. It doesn't do anything because it's already covered by the A. So basically what it's saying is anytime I have an expression that is ORed with another expression and one of those expressions is smaller than the other one, but the same, it goes away. And it extends more complicated a little bit. So let's say you had let me do that this way. X and Y or X and Y and not Z. Same thing happens. I have to have X and Y in order to have X and Y and not Z, right? So this expression has a Z in it, but it just doesn't care what Z is doing. And so that means that if I don't care what Z is doing here, why should I over here? So it goes away. And the other way to look at that in this case, which is really useful, is I can factor out the X and Y, which becomes 1 or not Z. And what is 1 or not Z? 1. So this not Z goes away. Yeah. So I hope that's like what 3 different ways to express the same thing. This is true of engineering all the time. You're going to run into situations that there's like 9 different ways to get to the right answer. Show me your work so I know what one you chose, right? It's fine. Okay. Now I need to introduce, I think, what is the last theorem that I have to teach at all. And the theorem is called De Morgan's theorem. And De Morgan's theorem is something of a nightmare. In its simplest form, it's really easy. And all De Morgan's theorem says is that not X and Y is equal to not X or not Y. And similarly, not X or Y is equal to not X and not Y. Right? That's all this is saying, right? Is that it's a Boolean expression of that gate equivalency. Right? I've just drawn what these gates are doing. So this is all De Morgan's is saying, which is anytime I have a bar over 2 terms, is I flip the gates, invert the terms. Okay, that's all De Morgan says. Now it becomes a nightmare when I have this back here, right, which is what I'm building up to. And so we need to be careful with this theorem, but this is why I waited for this one, because let's see, yep, I have enough time to do it, which is really, really cool. And we're going to go ahead and simplify this nightmare of a circuit. Okay. So the first thing that I'm going to do is realize that I'm an idiot and I should have probably just written this up here and erased everything else. And then instead I'm going to rewrite this there. Ooh, no, I'm going to change my mind. I'm going to do it this way. Keep that mess of a circuit in mind as I copy this down. Okay.
So real quick, the second term, it's X bar and double Z bar.
Not really,
No?
because what it is not X and Z, which the Z doesn't have a double bar on it because I'm not allowed to.
On that second term, you flop.
Yeah, no, that's what I'm
bar
saying.
needs to be above the Z, not the at.
Oh, did I?
Yeah,
Oh,
you just
I
messed
see.
up the- Yeah, sorry.
Oh, I thought you were asking a question, not
No.
correcting my mistake. That's fine. Thank you. Sorry.
Yeah.
Okay. Better. Yeah, I don't want to get confused because I transcribe something wrong, right? That'd be the worst reason to get confused. I'm glad you guys have no fear of speaking up, and I'm glad you guys are apparently understanding enough to call me out because it's important that I don't teach you wrong, right? It's like, what was it, the Panda movie that is we taught him wrong because it's funny. It's less funny when you guys are trying to get jobs out there. And I'm not, what the fun part is, I'm actually, but the exam, the first exam that you guys are going to get is actually modeled off of an interview that I had. I had an interview when I was an undergrad for On Semiconductor, which is a company here in Salt Lake. And they basically just gave me the exam that you guys are going to take because they want to know that you know how to do digital things. And so, anyways, my point is it's useful for industry. All right, let's start simplifying. And let's go ahead with the obnoxious De Morgan stuff first, because it's hard and it's new, and that's probably what we should start with. So this one's fairly easy, right? Because this follows exactly what I wrote over there without any confusion. So this term comes down, the X stays, and it's ANDed with, well, I flip the gate, which is currently an and if it helps, explicitly write it. So ands become ors become ands. Or, and I have not Y or not Z, right? That's just straight up easy peasy De Morgan's theorem. Well, let's do the less easy one, right? And I'm gonna refill this in because it kind of looks like maybe it was dashed and it's not. Okay, so what I'm gonna do is, eventually you'll do this in your heads, but for now, let's just explicitly call this A and this B, because we're not using A's and B's, so they're clearly different, and I've switched markers, so it's easy to follow. And now I have A or B, which becomes, well, the or becomes an and, right? And I'm gonna call this whole term A for now. So I end up with not A and not B, okay? And now I can go ahead and replace those, which is not X and not Z, and not Y. Yes.
So just a question. So with what we just did, could you,
Do all three at the same time?
so you can't put it not X, Z, Y, or you can't smash.
Let's test it. Let's do this first and let's go test that after, okay? So let's see this one. Now it's just De Morgan's again, right? So I end up with not X, the and flips to or, not Z, right? Because I had not Z and now it's not Z. So I added another not parentheses, not Y. This and not Y. Now, let's go ahead and, sorry, what's your name? You asked a lot of questions. I should probably learn it.
Brendan.
Brendan. Don't apologize. I'm terrible at names. I'm gonna try, but there's so many of you and I'm already bad at it. Yeah.
Wouldn't that, sorry, wouldn't that not Z just be Z?
Yes. Yes, exactly. The not Z. I like to draw it because it's clear and then it goes away. Either way is fine. Sometimes I would leave it until like the next row for it to go away just to show the work. I've seen enough Boolean algebra. If you just don't put it, I'll recognize your work, right? You don't actually have to do it. It's fine, but good catch. Yes. Okay, so let's go the other way, right? Let's just sample this and say X and not Z or Y. Okay, and now we're going to apply De Morgan's to all three gates and all three terms at the same time. Okay, so we get not X because we're flipping, or because this and has to become an or, Z because it's again not Z, and Y. Exactly. It is correct. You are allowed to do it, but it is super easy to mess up this stage. We need to recognize that anytime I convert an and to an or, I need the parentheses.
Okay.
Yeah.
Why is that Y not?
Oh, it is. Sorry. Not Y. Yeah. Sorry. Thank you. So it works, but anytime you convert an and to an or, put those parentheses there so that we don't accidentally think this is not X or Z and not Y, right? Those are very different expressions. So it's allowed, Brendan, but it's
Just make
a
sure.
risk. So I do it this way the first time because it's just a little bit more time and lower risk. And now this would come down. And this comes down. Great. So for me, I think the easiest way is I'm just going to turn this into a massive mess, right? I'm going to start foiling. In the meantime, so it turns out that's what I do all the time, right? Is I just turn it into the sum of products form because it's easier for me, and it's totally fine if it's easier for you. I won't judge you for doing that. As it stands, I could probably look at this cheat sheet, and I have a rule from table 4-9 in your guys' book that says the following. I'm sorry, I lost it. Those are equivalent. So can I apply that? Let's find out. I have not X or Y. Nope, didn't quite work out for me, right? So that one doesn't apply. There's a big complicated one. That's not in your book, so I'm not going to worry about it. There is actually a direct simplification for not X or Y, not X or Z, and that. So as long as I can start pulling those out, there's actually an easy simplification that I could cheat and do that with. But it's not in the book, so I'm not going to worry about it. So let's go ahead and I guess FOIL, right? That's probably the best way to start doing this. And we end up that, and now that. Not X, Y. Sorry, if this confuses, right? I'm just keeping them in alphabetical order. So this is the not X, Y, and now it's going to be Y, Z. And that's all with this not Y and or X. Correct? Great. So now we're going to have several simplifications, and we can multiply this through, right? So I'm going to end up with, so it's easier for everyone to see, I'm going to write that down up here. I'm going to do a couple of these internally so I can simplify my writing, right? Not X and not X is just not X. It's just that redundancy. Not X, Z, Y, Z, not X, Y. I don't see anything obvious to simplify yet on that one. Nope, we'll find out. All right, I'm going to just start copying down from there then. X, not Y, or term 2, not X, Y, Z, or term 3, not X, Y, not Y, term 4, right? Am I good?
You need a not over the not X and a not over the Y. In the very beginning, it should be not X, not Y.
Which term number?
That one, that one.
This one?
Should be not X, not Y.
Oh, okay. Any other mistakes?
Not X, not Y, Z.
This one? Thank you. As I said, I'm public speaking, right? Anytime you're speaking in front of the public, you're going to get distracted by the process of doing it. It turns out it's hard for me to talk and write at the same time, and yet I keep trying to do it. I'm fallible. All right, let's start looking for things that are easy, right? And the easiest one is anytime I have Y and not Y, it goes away because I can't, it's just 0 and or with 0. So that goes away. Y and not Y goes away. Great. I would like to find, if I could, something that was like not X and not Y. not X and not Y. See how I have this term
Yeah, and then
and that, and it's, so it doesn't care about that Z, so this whole term is redundant. Goes away. Now let's bring these down because I cancel out a whole lot and it's helpful to rewrite. A lot of the mistakes that you guys are going to make when you do this Boolean algebra is going to come from arrogance of, oh, I don't need to rewrite this. I can keep canceling just fine. Don't be afraid to rewrite. You will, despite it taking time to write this down, it will save you time in the long run just to do it right. Now we look at this, and now we've got some fun, I guess we could say. Right, it's pretty safe to say that I don't think this is going to simplify if anything, because I have no more not Z's or Z's at all. So now I'm just going to focus on this one. And what do we have?
take the X's out.
Yeah, so we have this not Y that I can factor out, which is not X or X, which is, that's just exactly, it's just one. So I have not Y or X, not Z. And that's my final circuit
A lot more simple.
compared to the giant mess that I had erased before. Well, half erased anyways, right? Yeah.
So when you have like at the very first one, you have not X, not Y, plus not X, not Y, Z. So if you cancel out that second one, it just cancels the whole thing out, like, because the Z doesn't matter, right? Is that what you're saying?
Yes, exactly. Yeah. Because this term is redundant to that term.
Because it needs not X and
Yeah.
not Y.
It's the same thing as saying is this. Not X, not Z is equal to not X, not Z, or not X, not Z, right? This is redundant. So this is easy to see that it goes away. It just so happens that no matter how many additional things I and this with, it still goes away. Because of this, right? Because it factors out and then simplifies, basically, is what happens.
Basically, that's an or gate with two inverters on it, on the input.
This one?
No, the other one, the one you just finished up with.
Oh, this one. Yeah, well, we could design this circuit, right? That's the whole point of this, is we're going to analyze a big mess and then let's design. I think I have time. Sweet, I do. Let's design it. What is my output gate? Or. And I alluded to that, right? I said if I FOIL, I'm going to end up with sum of product style terms. Okay. The OR gate, well, one of those terms is simply Y through an inverter. And then the other OR needs an AND, right? And now I have X, not Z. Well, X goes here, Z goes here. I go through an inverter. That's my circuit. And now I ask the question, convert this to a universal gate circuit. Yes.
So if we're in the Boolean algebra and we want to convert it from universal gate, could we use, because we have like not Y plus X, not Z. Could we go back on the thing that we did previously? Does that make sense? Where we had the OR and we go back and make it.
Yeah,
not
so
and, or an and.
so let's do,
You kind of know what I'm saying?
yes, I think I do. And I'm going to illustrate it a slightly different way.
Okay.
Let's say we have this, okay? And I'm not happy having a NAND universal gate. Well, is that a not? I've artificially inverted it, right? but that's fine. And now I say that this is equal to not y, which is just y, and not z, not x, sorry. Not z. Right? And now what I've done is this is equal to that, but this is not equal to this, right? Because if I call this output function f, right, then this output function is not f because I've inverted it. So what I have now here is a product of sums expression, right? Because my output gate is an and, but I have an inverter on it. So if I go and build this gate, that's my circuit. But this is for F bar, right? Throw an inverter at the output and take me one more gate, and I fixed it all. Right?
You can push that inverter to the left and then get it. And you get it.
I could, exactly. If I decided I wanted NAND gates, then I could turn these into NAND gates. This one gets a little bit weird because I push this bubble into here, right? And then this is still not a NAND. So I would like push this bubble up against the OR and then put an inverter here. Does anyone wants, I'll just do it. So I push this bubble that was on the inverter here. Now that's a NAND. This is, well, I want this to be a NAND, so I'm going to add 2 bubbles at the input. In order to keep it the same, I need to push bubbles along. Well, one of those bubbles runs into this inverter and cancels out, right? Because not is the same thing. And then I push a bubble here, but there's nowhere for it to run into. I just add an inverter. And now they're NAND. Or I could leave the inverter and turn it into NORs.
But what's the value in changing it from a NOR to a NAND?
Oh, the benefit is depending on your technology, you may have one or the other. So like if you go out, the most obvious example is if you were to go out and buy memory for a computer or something, and I don't mean like your desktop because that's all pretty standardized at this point, but like if you were designing a chip and you needed some memory on it, right? You would go out and you would buy memory and it's going to either be NAND flash or NOR flash. And each of those have different benefits. There's trade-offs between the two. But if you're building a integrated circuit, something large that has a bunch of these, you want to use all of the same technology. So you say we have NAND gates because that's our memory. Now you have to design everything out of NAND. So anything that would have been NOR, you have to convert or vice versa. So we have to keep in mind that it's just scale basically is anytime we have a lot of something, it's cheaper. So we want to execute our technology in all NAND gates or all NOR gates. And so that's what happens. It's just the benefits of mass production.
Yeah.
So that's why we convert it. I'm gonna call it there. I think that's plenty.
I guess the sum of that would be China likes it better.
Sorry, what's that?
China likes it better.
Oh, yeah. Yes, exactly. Although more and more integrated circuit design is being moved back to the US because the people are sick of property theft, intellectual property theft. No, it's wonderful for us.
Yeah. About right.
Yeah.
Yeah. We need that.
Yes, it's quite wonderful. Yeah,
You said Monday we're going to the lab, or yeah, Monday.
yeah, we should be in the lab.
Yeah.
Yep, yeah, we'll be downstairs on Monday. I'll send an announcement as long as my brain doesn't forget. I'll write it down actually. So I got it. Yes.
So, I was looking at projects about what copy going with my making.
Yeah.
I know it's constantly about a senior project, and I'm going to be a senior next semester. I was wondering how that all kind of works.
Oh, yeah. So in order, you don't have to worry about it yet.
Yeah.
The senior project really means a senior within the major. So you'll register for that once you're further in the program.
Okay.
Because in order to register, you actually have to be admitted to the professional program is what we call it
Yeah.
anyways. And you have to have finished a certain number of junior level classes because the senior project expects you to implement things that you learned in your junior level courses.
Yeah, that makes sense.
Yeah, so, yeah, don't stress about that yet. There's you are a senior because you've taken other classes or have AP credits or whatever it happens to be. And then there's the standing within the major and they're
Okay.
disconnected.
Okay,
It gets confusing, so, but don't
so,
stress.
so I'm a freshman within my major, but I'm a senior by credits.
Yes.
Okay, awesome.
Yeah.
All right, thank you so much.
I just got a question.
Yeah, go for it.
We did this question here. So I grouped them. For the. So you see how I grouped them?
Yes.
Those two, then the middle two.
Yep.
And I still came out with,
Hey, is that what we got?
Yeah.
Yeah, then you're fine.
okay.
Yeah, there's gonna be, right, that was when I started the example right before this one, how I started pointing out that there was like 3 different ways that we can start simplifying it.
Yeah.
All of them would end up at the same expression as long as we did it right. So there's no wrong way as long as you follow the rules.
Okay. And then is that how you would draw the? gauge
B
for that?
and A or B. Yeah.
Sweet. Thank you.
And you can always use the analysis techniques. After you design the circuit, you can apply your analysis to it to see if it makes sense.
Okay. Well, thank you.
Yeah.
Two things. And when I submitted my assignment, I had a comment, because like my scan was being weird. It was like it was showing some things and wasn't showing. I was wondering if you saw that.
I haven't graded it yet.
Okay. Because it was like, I kept it just in case, because it wasn't, sometimes it wasn't appearing all the way, and I think it just might have been the paper,
Okay.
but I
Yeah.
kept it just in
I'll
case.
send you a message
Okay.
if it's
Like
fine.
not readable.
Yeah.
And then, so I was really struggling with this not A, not B, and C for the Venn diagrams.
Oh, okay. Yeah. Sorry, let me see. What's your question about? I just want to see if it's quick. Do
No, it's not good.
you have a question?
I think,
Yeah,
sorry.
Is it quick or is it?
I think it's quick.
Okay, what's the question?
So, so I was scared COVID last week, so I was here on Wednesday for lab.
Yes.
Is there something I can do at home with that lab, or are we continuing it on Monday?
Yes,
From-
send me an email
Mhm.
telling me that you haven't been and I'll send you some information.
Cool,
That's gonna be
sounds
the easiest way to do it.
Cool. I'll do it now.
Let me go stop the recording. I don't think I need to keep this running.